Hello, it's Micah. I'm going to be doing a video about waves. I'm going to try to move kind of fast because I don't have a lot of storage on my phone. Um, but anyways, I want to start with a definition of what a wave is. A wave is a flow or transfer of energy in a form of an oscillation through a medium or medium, space, or mass. All right. There are three types of waves. There's mechanical waves, electromagnetic waves, and matter waves. A mechanical wave is a wave that is an oscillation of matter and is responsible for the transfer of energy through a medium. There are three different types of mechanical waves. There are longitudinal waves, transverse waves, and surface waves. A longitudinal wave um, uh, is the movement of the particle that are parallel to the motion of the energy, um, and I'll explain that in just a second. The displacement of the medium in the same direction to uh, which the same direction to which the wave is moving. An example of this would be a sound wave or a pressure wave. Also, how it looks too. Imagine like a slinky, and you have a slinky in maybe like a line, and you're holding on and you're sort of maybe jolting it and thrusting it forward. Um, you'll see the waves sort of condense and move along, and that's the premise of a sound wave or a pressure wave. There's also transverse waves, which transverse waves is when the movement of the particle is at right angles or perpendicular to the motion um, of the energy. Then this type of wave is known as a transverse wave. Light is an example of a transverse wave. And when it means by the particle is at right angles or perpendicular to the motion of energy, it means for transverse waves the motion is going up, right? Um, and the velocity here. This is a picture of a transverse wave right here. That's a transverse wave, and you see the direction of it is going up, and the velocity of the frequency of the oscillations moving um, make it so the direction is going that way, and the wave is going up, so it's perpendicular to each other. Now, with longitudinal waves, it's more like a slinky, right? So that same example of like jolting or thrusting the end of a slinky that's in a line, um, you see um, the direction and the wave direction and the direction of energy and the wave of energy are going in the same direction. They're making them parallel to each other. Um, the this and then the third type of wave from mechanical waves is surface waves. Surface waves means the particle travels in a circular motion. These waves usually occur at the interfaces. So when uh, it interacts, um, waves waves are um, waves in the ocean are examples of this. Ripples in a cup, like an experiment that I did where I dropped the drop of water and made the ripples. The second type of wave is the electromagnetic wave. A electromagnetic wave is created by a fusion of electric and magnetic fields. The light we see, the color that's around us, are visible because of electromagnetic waves. Examples of electromagnetic waves are microwaves, X-rays, radio waves, and ultraviolet waves, which I'll talk about later. Then the third type of wave is matter waves. Matter waves is really an idea or concept that explains that the dual nature of matter, its ability to both exist as a particle and as a wave. This was first brought up by the founders of the field of quantum physics, because physicists realized that these can't be explained using Newtonian physics, so they developed a whole new field. An example of this is maybe like a beam of electrons can be diffracted, which I'll show that in a minute, just like any other beam or of electromagnetic radiation or water wave. So this is basically the basic. This is the premise of diffraction. There's a split. These would be the small particle, or these would be the particles, and being diffracted into a larger split and creating a less intense wave. Now there's the particles right here going forward and a smaller split and creating larger waves in a larger direction. And I also wanted to talk about how you measure waves or how you can measure oscillations. So as you can see in this wave, you have, this is mirrored so you can't actually read it, but this is the wavelength, this is the amplitude, and this is the frequency, and then that's the time right there. So the amplitude is the height of the wave crest, or the depth of the wave trough, that's the bottom. From the middle, it is the measure of energy a wave carries. Wavelength is the distance from a wave crest to another. And then the frequency is the number of wave crests passing a fixed point. And then period, or time, is the time it takes for one complete oscillation, which is one up and down. And also, and this is what, you can't read it, but this is a basic picture of a electromagnetic wave. The blue is a magnetic field, a blue is a magnetic field, and a red is the electronic field, and then the black arrow is the direction it is moving. And also I want to talk about the color spectrum right here. Can't read it, but color spectrum right there. So radio waves, like I said, radio waves AM, that's on Earth, can travel very long distances and are not very energetic, not dangerous, and travel at much lower hertz. Microwaves are can be travel a shorter distance, but carry more information. That's actually what my phone is using right now, and your device to watch this video, transmitting the information. Infrared is used. We also can't see that, but we use that in. I know we use that in chemistry to make certain measurements. Just because we can't see in that wavelength. Then of course there's the red, white, or red, white, and blue. Red, orange, yellow, green, indigo, violet. Um, in elementary school, it was just blue and purple, but indigo, violet, and then there's ultraviolet light that comes from the sun, and that can be harmful. I mean, you could get sunburn, get welts. Some people are allergic to ultraviolet light, or uh, just burn easily. And it's more energetic, and more dangerous than, say, a microwave or a radio wave. Um, X-ray, that can be harmful over time, but that can penetrate your tissue, but not your bone, and that carries even more energy, and can be dangerous over a long period of time of constant exposure. That's why radio technicians, or not radio technicians, X-ray technicians have to stand behind a wall, because they would be exposed to too much radiation, um, and that's why you can only get an X-ray when you're hurt and not just whenever, um, because you'd be increasing your chance of cancer and other problems, weird mutations. Excuse me. And then gamma rays are even more energetic, extremely energetic, and can be very, very dangerous. They go straight through your body, destroying cells and leaving behind a lot of a lot of radiation, um, causing mutations, which in turn causes cancer, because that's what cancer is, mutation. Um, these the more dangerous and the higher frequencies you get, the smaller the wavelength, um, and the more energy it can carry with those oscillations. Um, but anyways, and okay, I guess that's the end of it. There's no grand finale, I guess. I hope you. I hope this satisfies what I need, and I really hope this works. Please let me know if it doesn't. But anyways, have a good rest of your day, and see you around.